Molecular orbital theory. The valence bond theory accounts for qualitatively for a stability of a covalent bond in terms of overlapping atomic orbitals or hybrid orbitals, but it does not account for the observed properties of many of our molecules. For example, we think oxygen, when we draw the Lewis diagram, we draw oxygen with a double bond and then 4 sets of lone pairs, so all of our electrons are paired. So it should be diamagnetic, but in fact it's paramagnetic. So you can see in the picture we have arrows going the same way, so we have 2 unpaired electrons. So something that you're going to have to remember from another unit, diamagnetic is repelled by a magnet. All of our electrons are paired. That's what we think oxygen should be, but in fact oxygen is paramagnetic. It's attracted by a magnetic field, so you have 1 or more unpaired electrons. So what you're looking at in the picture is this oxygen between the magnets, and you can see that it kind of bundles up and it's attracted to the magnets instead of going right through. So the molecular orbital, or MO theory, describes the covalent bonds in terms of molecular orbits. Molecular orbits result from the interaction of atomic orbitals of the bonding atoms and are associated with the entire molecule. Bonding and anti-bonding molecular orbitals. So bonding orbitals are those at lower energy and greater stability than the atomic orbitals from which it was formed, or the stable, so it's the stable bond. Anti-bonding orbitals have higher energy and therefore lower stability than the atomic orbitals from which they're formed. So that would give us an unstable bond. Sigma molecular orbitals, the electron density is concentrated symmetrically around a line between the 2 nuclei. Where a pi molecular orbital, the electron density is concentrated above or below the line joining the 2 nuclei. Okay, so if we think about hydrogen, H2, each hydrogen atom is contributing 1 electron, and both of those electrons would fill the sigma 1s. So they're paired in the sigma orbital. So we still follow the same rules that we follow when we do electron configuration, like the Pauli exclusion principle, where we have to have 1 arrow up, 1 arrow down to show the opposite spins. Electrons in the anti-bonding sigma orbital have higher energy, less stability than those in the isolated atom. Electrons in the bonding orbital have lower energy, therefore more stability. So to understand the properties of molecules, we must know how electrons are distributed among molecular orbitals. So there's some rules. The number of molecular orbitals formed is equal to the number of atomic orbitals combined. More stable the bonding molecular orbital, the less stable the corresponding anti-bonding orbital. And you fill from the lowest energy to the highest. Each orbital can accommodate 2 electrons, but they have to have opposite spins, so that's Pauli exclusion. And when you put orbitals in the same energy, you would put 1 in each orbital before you would pair up, Hund's rule. They would also have to have parallel spins to have the lowest energy. Number of electrons in the molecular orbitals has to equal the sum of all the electrons in the bonding atoms. Bond order is 1/2 times the number of electrons in the bonding molecular orbitals minus those in the anti-bonding molecular orbitals. The bond order indicates the approximate strength of a bond. The stronger the bond, the more stable it is. The bond order could be a fraction. The bond order of 0 or a negative value means the bond is unstable, and therefore that molecule cannot exist. So if you think about the Aufbau principle, where we have that diagonal rule in that chart to show us our filling, this would be the molecular orbital version of the Aufbau principle. So you have your 1s, where you have sigma and then anti-sigma. Then you would go to 2s, sigma, anti, and then you would fill the 2p. Now 2p has 3 orbitals. 2 of them are pi, 1 of them is sigma. And then you have your anti-pi and your sigma, anti-sigma. So using this filling diagram, we can actually start writing electron configurations. So Li2, if we have 2 lithium atoms coming together, they would have sigma 1s squared sigma 2s, 1s antibonding squared sigma 2s squared. If we look at B2, we don't really need to continue to do the 1s because we're really only looking at valence electrons. So let's jump to just valence electrons. So for boron, we would have sigma 2s squared, sigma 2s anti, and then pi, 2p pi squared. And you can see how it goes. So if we do fluorine, F2, we would have sigma 2s squared. You can put parentheses around it if you want. You don't have to. Sigma 2s anti squared, sigma 2p squared, pi 2p to the fourth, because remember there's two orbitals there. And then we have the anti-bonding to the fourth. So if we want to calculate bond order for F2, we would say 1/2 bonding 2, 4, and 4 make 8, minus the anti-bonding 2 plus 4 is 6. So 8 minus 6 is 2 times 1/2 gives us a bond order of 1. So that is a stable bond. Let's do the same thing, but let's do F2. So F2 would be sigma 2s squared, sigma 2s anti squared, pi 2p squared, well, to the fourth because there's two of them, sigma 2p squared, anti-pi to the fourth, and then sigma 2p to the first, anti-sigma, because we added an extra electron. So the bond order would be 1/2, 2 plus 4 is 6, plus 2 is 8, minus 2 plus 4 plus 1 is 7. So this gives us a bond order of 0.5. Fractions are okay. So the magnetic properties, is this paramagnetic or diamagnetic? Because I have a lone pair or a lone electron, this is going to be paramagnetic. I have an unpaired electron. So is the bond length longer or shorter than for F2? Well, the bond order is less, and since the bond order is less, F2 minus is weaker, which means the bond length is longer. Delocalized molecular orbitals. So we have something special happening with some of our resonance structures. So if we think about benzene, which is C6H6, we would have a chain or a circle of carbons with hydrogens attached. So this first picture is just showing you the sigma bonds. All carbons are sp2 hybridized, so the 2pz orbitals are actually perpendicular. So we have some of the double bonds happening. But notice all of them are perpendicular, so they're all in this ring together. That means that double bond can float in between all of my p orbitals. So if you look, it's kind of hazy throughout the entire thing. This is our top view, and then we have our side view. So we have electrons hanging out above and below that perpendicular line. So the interaction of the 6 orbitals leads to 6 pi orbitals, 3 bonding, 3 antibonding. The delocalized molecular orbitals then are not confined between the 2 adjacent bonding atoms, but actually extend over 3 or more. So we have this extension of this ring, so it kind of, those double bonds float in between. And we have a resonance structure. So the electron density shown here shows that red region above, and there's a red region below the ring. So the compounds with delocalized molecular orbitals are less reactive, therefore they're more stable. So benzene is a very stable molecule. Now another one that has these delocalized molecular orbitals is the carbonate ion, or CO3. We have a double bond occurring So it extends over all 4 of my molecules. So we could have the double bond here, we could have it between those two, or we could have it between these two. So we have this region of electron density above and below the plane. So it makes it a little bit more stable and therefore less reactive.